Ladies and gentlemen, my name is Xiao-zheng. I'm from Institute of Oceanographic Instrumentation, Qilu University of Technology, Shandong. Academy of Sciences, Qingdao, China. The title of my thesis is Synchronous Monitoring Method of Multi-Manipulator Trajectory Signals Based on Machine Learning. Abstract. The traditional trajectory signal monitoring method uses a combination of sensors and mathematical models to detect the trajectory signal of the manipulator, which is susceptible to interference from uncertain factors, resulting in low monitoring accuracy and poor real-time performance. In response to the above problems, this research designed a method for synchronous monitoring of multi-manipulator trajectory signals based on machine learning. After the multi-manipulator dynamic model is established, the coordinate system of the trajectory acquisition equipment is calibrated according to the principle of binocular vision. After pre-processing the trajectory image of the manipulator, the CLDNN model is used to realize the synchronous monitoring of the trajectory signal. The simulation experiment results show that the monitoring method shortens the monitoring time by about 62.5%, and has higher monitoring accuracy, which proves that its performance is better. Keywords. Introduction. A mechanical arm is an automatic operating device that can imitate certain actions of a human arm to grasp, carry objects or operate tools in a fixed program, and it is an important branch of industrial robots. The robotic arm is an important equipment in automated production, with the advantages of high safety and long working hours. After more than half a century of development, the control accuracy of industrial manipulators has been continuously improved, its types have become more and more abundant, and the application fields have also continued to expand. There is a strong coupling between multiple manipulators, so although there are independent controllers for each mobile manipulator should not be controlled separately, but should be considered as a whole one. It is an effective way to improve the control precision of multi-manipulator to monitor the error between its moving trajectory and the theoretical trajectory of control instruction when controlling multi-manipulator. Method design. Multi-manipulator motion analysis and dynamic modeling. In order to be able to monitor the trajectory signals of multiple manipulators simultaneously, a mathematical model of the multi-mobile manipulator system must be established first. Usually, a fixed coordinate system is defined on each link of the robot arm, and two adjacent coordinate systems can represent each other, and their relative positions are generally described by the transformation matrix between the two adjacent links. The connecting rods are numbered starting from the fixed base of the robotic arm. Generally, the coordinate system at the fixed base is, and so on, so the coordinate system on the connecting rod is. For the robotic arm, the coordinate system of all links can be established in sequence according to the following steps. 5. Find out the corresponding joint axis of each link and extend it in the direction of its axis. In the formula, represents the trajectory of the end of the robotic arm in Cartesian space, and represents the rotation angle of each joint of the robotic arm in the joint space. Take the derivation operation on both sides of formula 1 to time respectively to obtain the relationship between n as shown in formula 2. In the formula, is the speed of the end of the manipulator in Cartesian space, is the angular velocity of the joint rotation of the manipulator in the joint space, is the Jacobian matrix of the manipulator. The elements in row and column of the matrix are. The multi-manipulator dynamic model studied in this paper is obtained on the basis of the Lagrangian function method. The kinetic energy K of the system is defined as the sum of the translational kinetic energy and the rotational kinetic energy of each link, and its expression is as follows. 4. The potential energy P is defined as the sum of the gravitational potential energy of each connecting rod, and its expression is as formula 5. Trajectory acquisition equipment dual target positioning. The pinhole imaging model of the camera actually uses the above geometric relationship constraints to simulate the image formation process, that is, to establish the coordinate conversion relationship between the two-dimensional image collected by the binocular camera and the three-dimensional objective object. The ideal imaging model of the camera is the pinhole imaging model, which does not consider the distortion of the camera in reality. There are four coordinates in this model: the world coordinate system, the camera coordinate system, the image coordinate system, and the pixel coordinate system 7. In an ideal camera imaging model, the default pixel plane is parallel to the image plane, and the pixel coordinate system is known, that is, the coordinates of point in the two-dimensional digital image, and then the points of pixel and world coordinates are derived, in turn the derived relationship between. Due to the manufacturing process of the camera, it cannot guarantee that the imaging plane of the camera is absolutely perpendicular to the optical axis of the camera. From the imaging situation of the camera under ideal conditions, the mathematical derivation of the generalized pinhole imaging model can be derived as follows. Robotic arm trajectory image processing. According to the brightness component of the pixel in the robot arm trajectory image, the conversion relationship between RGB and YUV color space is constructed as shown in the following formula. A. In the formula, is the position of any pixel in the image, and correspond to the weights of the three color components of R, G, and B in the RGB color space, and are the brightness values of the three components of the image, is the grayscale value of the image after grayscale conversion. After converting the image gray level, a Gaussian low-pass filter is used to process image noise. For image denoising processing of size, the transfer function of the two-dimensional Gaussian low-pass filter is as follows. In the formula, is the image pixel of the input Gaussian low-pass filter, is the filter transfer function, is the distance from the center of the frequency rectangle, is the variance of the image gray value. Image denoising processing will result in blurring of the edges of the image. Sobel operator is used to detect the edges of the image. The calculation formula of Sobel operator is as follows. 9. In the formula, is the image gradient, is the image gradient amplitude, is the image direction angle. After image pre-processing, the image is transformed from the spatial domain to the fuzzy domain according to the following formula. In the formula, is the gray value of the image, is the membership value of the fuzzy domain of the image, is the local image contrast, which is also the fuzzy enhancement operator, is the inverse transform function of the fuzzy domain, is the fuzzy parameter of the fuzzy enhancement. Generally, in order to obtain high-definition images of the robotic arm trajectory, the camera needs to continuously shoot multiple high-definition images. In order to improve the efficiency of track signal monitoring, the image is compressed. Image compression processing. After processing the robot arm trajectory image, the plot compression algorithm is used to compress the image signal to reduce the image processing dimension. The essence of the plot compression algorithm is to find all the main trends in the collected signal, and use the segmented linear trend to replace the original collected data to achieve the best possible data compression effect. For the prediction time series object, suppose its model is a discrete time signal sampled at equal intervals as shown in equation 15:10. Realize the simultaneous monitoring of multiple robotic arms trajectory signals. This paper constructs a CLDNN model accordingly. The structure of the CLDNN network is to connect several layers of CNN after the input layer to extract local features. The output of the CNN is poured into several layers of LSTM units to reduce time domain changes. The output of the last layer of LSTM is input to the fully connected layer. With the purpose of adding features, the space is mapped to an output layer that is easier to classify. After the convolutional layer, the BN layer is deployed for normalization to avoid overfitting. The fully connected layer connects all features and transmits the output value to the softmax classifier. The following cross-entropy loss function is selected as the loss function of the model. Test experiment. Experiment content. This experiment is a comparative experiment. The synchronous monitoring method of multi-manipulator trajectory signals based on machine learning studied above is used as the experimental group, and the traditional trajectory signal monitoring method is used as the comparison group. By comparing the error and response time of the two signal monitoring methods, the reliability of the monitoring method studied above is verified. Experimental environment. The experimental platform includes Denso VP6242G and Quanzer's Open Structure Control Module. The control module has the functions of all industrial systems and serves as an interface for interaction with the Quark software. The closed-loop frequency of the controller is 4 kHz. Users can adjust the gain of the controller through the Quark software, or design their own controller in the simulation environment, and directly use the completely open commands to bypass the internal PID controller. The experimental platform realizes the rotation of each joint through the servo motors at the joints and is equipped with corresponding measurement sensors. The measurement data controller and the Quark software interact to realize the reproduction of the end trajectory of the manipulator. Experimental result. The comparison results of the two trajectory signal monitoring methods to monitor the trajectory error of the multi-manipulator are shown in Figure 1. From the analysis of Figure 1, it can be seen that compared with the error change curve of the contrast group, the monitoring error of the method in the experimental group for the trajectory of the multi-manipulator is significantly smaller. Although the monitoring errors of the two groups were within the allowable range, the fluctuation of the monitoring error curve of the contrast group method was significantly more severe than that of the experimental group. Therefore, the monitoring performance of the proposed method is better. When the two methods are monitoring the trajectory of the same parameter manipulator, the response time of the monitoring method is shown in Table 1. By analyzing the data in Table 1, it can be seen that the response time of the method in the experimental group in monitoring the trajectory signal of the manipulator is less than that of the method in the contrast group. After averaging the data in the table, it was found that the average response time of the experimental group method was 7.035 milliseconds, and the average response time of the contrast group method was 18.745 milliseconds. The above results indicate that the trajectory signal monitoring method studied in this paper has higher monitoring accuracy, real-time performance, and better performance. Concluding remarks. Industrial manipulator is an industrial automation equipment which includes machinery, communication, automatic control, computer, and other disciplines. It plays an important role in high-end manufacturing industry. In order to improve the control accuracy of the manipulator, this paper studies a multi-manipulator trajectory signal synchronous monitoring method based on machine learning in view of the problems existing in the traditional trajectory signal monitoring methods. Based on the establishment of dynamic model of multi-manipulator, this method calibrates the coordinate system of trajectory acquisition equipment by using binocular vision principle. Then, after pre-processing the trajectory image of the manipulator, the CLDNN model is used to realize the synchronous monitoring of the trajectory signal. This study also proves that the method has better performance through experiments.